so Stephanie's going to be taking video for us. So what we're going to do today is we're just going to try to run through rather quickly a lot of the concepts and equations and things that you should be studying for the final exam. So just as a reminder, so there's two different sections of this course. There's some people probably from each class in here. If you're in section 801, your exam is on Monday at 10 a.m. Try to get there a little early, right? That's if you met with that's if you were in the 11 a.m. class. If you were in the 3:30 class, then your exam is on Wednesday at 12:30 p.m. next week. Okay. Just as another little announcement, so I posted the practice exams on Canvas earlier this week. I just posted the correct answers to those questions as a reply to each of those messages on each of your respective Canvas pages. So if you go and you want to see the correct answers to the practice exam, you can take a look at that reply that I just posted a few minutes ago. Okay, so let's run through what we're going to do, what we did this past semester. I should say not what we're going to do, what we did this past semester. All right, starting from vectors. All right, so vectors are always given this notation with a little arrow over the top of it. And one of the things that we did was the summation of vectors. And if we have a summation of vectors, then we add up the components. AX plus BX times I hat plus AY plus BY times J hat plus AZ plus BZ times K hat. Right, where each of these little hat things are unit vectors with a magnitude of 1 in a direction in the X, Y, and Z direction for I, J, K. And just as a reminder, so even if you're here, if you want to take notes on this, that's absolutely fine, but I'm going to post these pages that I'm writing down to Canvas when, after the review session. So you'll be able to just download this as a PDF. So you don't necessarily have to copy down everything that I'm writing. So it's probably a better idea to maybe listen a little bit more than you're actually writing. If you want to write something down, that's perfectly fine, but like I said, I will send these notes to you later. Okay. So that's the summation of vectors, right? And we also know that if I take the sum of vectors, that it's commutative, right? So if I add vectors in A to B, I can also add B to A. So it doesn't matter which order I do that in, right? And that works graphically as well. I'm not going to draw it graphically because it's going to cut into time for other topics, but I think that you probably remember that. However, if we have A minus B, that gives us AX minus BX plus AY minus BY times J hat plus AZ minus BZ times K hat. And that is not commutative, because if I take A minus B, that's equal to the negative of B minus A. So it does matter what order I do that. In the same way that subtraction is not commutative for numbers, it's not commutative for vectors. All right. And so then there's a couple other things we did with vectors that are very important. Certainly you have to remember the scalar or dot product. And so the way that works, right, is that the result of these two vectors being multiplied by each other, and it's always symbolized with a little dot in between them, is that I get scalar out. So instead of producing a vector the way I did with addition, I get a vector out of vector addition or a vector out of vector subtraction. I get a scalar. So in other words, it just has a magnitude and not a direction. And it's in the magnitude of that resulting vector is AB cosine phi, where phi is the angle between those two vectors. All right. And alternatively, if I have components, I can do AX times BX plus AY times BY plus AZ times BZ. And that would also give me the magnitude of the scalar product. Okay. All right. We also had another way of multiplying vectors, and that was the vector or cross product. And that's always symbolized by an X as a multiplication between the two vectors. And I'm not going to go through the full set of the terms that you get from that, but you can determine the cross product by using determinants. So I, j, and k across the top, and ax, ay, az, plus bx, or excuse me, and dx, by, and bz across the bottom. And then in order to determine the terms, right, I would cover up ax and bx to begin with, right, and then I multiply the I hat, the unit vector, times ay times bz minus by minus by times ac, right, and then go through that. If you don't remember how to do the determinants, I'm going to ask you to just go take a look back at it in either a math textbook or you can find it in all sorts of places online. Because it'll take a little bit longer to go through that. At the same time, the magnitude of the cross product, so when I draw these little vertical bars around that, that's not the absolute magnitude. That's not the absolute value, it's the magnitude of this vector. The resulting vector, right, because this gives us a vector and not a scalar, is AB times the sine of the angle between these two vectors. And then if I want to determine the direction of the cross product, the resulting vector of the cross product is given by following the right-hand rule. What do I mean by the right-hand rule? Well, I take my fingers on my hands and I point them in the direction of the first vector, and then if I curl them in the direction of the second vector, so say I have one vector that's pointing over here to the left, right? And then I have this is my second vector is pointed out towards you in the audience. I would take my fingers, point it first in the direction towards the left, then curl towards the audience, and then my thumb with my right hand points in the direction of the resulting vector. Okay? So make sure you don't use your left hand for the cross product. Always the right hand. All right, so that's vectors. That's the vector stuff that we use. All right, and some of that will become useful for some of the other things that we're going to do a little bit later. All right, so let's move on to a different topic. One-dimensional motion. So in 1D motion, we have this universal equation. X is equal to x0 plus v0x times t plus 1/2 ax t squared, which should hopefully be burned into your memory at this point by now. Right? And this is position is equal to initial position, which is x0, plus the initial velocity in the x direction, v0x times time, plus 1/2 the acceleration in the x direction times time squared. Right? We use this equation to describe the position of some object that has some constant acceleration, or potentially some varying acceleration over time. And from that, we could also get an expression for v of x. That would be v0x plus axt. Hopefully you remember that the relationship between these two equations is that the second equation is the derivative of the first equation. I'll also mention, too, that in free fall, so if we drop something, the acceleration in the y direction, which is also one-dimensional motion, just for the other dimension instead of the x direction, the y direction, is just minus g. Right? For most problems, we assume that g is constant. We're not talking about distances that are so far from the surface of the Earth that we actually have to have some variation in g. So we can just assume that g is constant, and that's our constant acceleration down. We drop something. Okay. So if we have some situation where we want the average velocity and not the instantaneous velocity, because this is an instantaneous velocity. So say we want the average velocity in the x direction. That's given by whatever change there is in the displacement over the change in time. And if we wanted the average acceleration over that time period, we could also do something similar for acceleration, which is equal to change in vx over that change in time as well. However, if we want the instantaneous velocity and instantaneous acceleration, which are not the same, then we have to take the derivative. So dx is equal to dx dt, and a sub x is equal to dv dt, which is also equal to d squared x dt squared. All right. So hopefully everybody remembers that at this point. All right. So by the way, so I know this stuff is pretty straightforward because we've been doing this a lot. But if we get into stuff a little later on that you have any questions about, interrupt me. I may not look up very much, so maybe just give me a holler if you have a question. All right. So we also did 2 and 3-dimensional motion. So this is just in 1 dimension, but if we extend that to 2 and 3-dimensional motion, then instead of x, we have some r vector, which is some vector that is a combination of x in the I hat direction plus y in the j hat direction plus z in the k hat direction. So that's our position vector, right? So that's telling us where we are in 3-dimensional space, or potentially 2-dimensional space, right? We could have just 2 of those components instead of all 3. See if I can focus this a little bit. No, that's worse. All right. I guess that's about as good as it gets, unfortunately. All right. Okay, so that's our position vector. So instead of x or y, now we have r, and r is a vector, right? And if we wanted to find the average, now if we wanted to do the same kind of average again, in this case we could do v average is equal to delta r delta t. This time we get a vector out of that. And then the average acceleration vector is given by delta v delta t. And then again, if we wanted to do instantaneous, we just take the derivative. So dr dt and dv dt, or d squared r dt squared, for the acceleration. Okay. And so we have a similar equation of motion as well for r, but instead of x, x0, v0, x, and all these things, right, we have r is equal to r0 plus v0x, which is also a vector, plus 1/2 ax, or excuse me, a sub r, right, which would also be a vector, but potentially changing in time. And all of these things could be functions of time as well. Right? So when we take the derivative, we may also have time terms that show up in our expressions for a and our expressions for b. Okay. So moving on, we also talked a lot about uniform circular motion. So in other words, I have something traveling around in a circle at a constant speed, right? So at any point on the circle, it's got some velocity v, and it has some acceleration a towards the center of the circle. And that's a radial acceleration, so the magnitude of that radial acceleration is equal to v squared over r, where r here is the radius of that circle. You can also alternatively express that as 4 pi squared r divided by t squared, where t is the time it takes for whatever we have to travel around the circle once. We can also get an expression for the speed of that object around the circle, which is just 2 pi r over t. And the speed is really just the distance over time. So the time, the big T over here is the period, so the time it takes to go around all the way around the circle once. And this is the circumference of the circle. right? So I'll go